Okay, so I'm going to give a brief introduction to pandas. It is something that is very useful in statistics. Um, to start off, pandas is a library in Python, normally imported as PD, the abbreviation. Um, and it's sort of a form to represent data. It's a data structure similar to a CSV or an Excel file. So let's get started here. We're going to import these libraries. We're going to generate some fake data just to show how to create a data frame using an actual series of data. So first we're going to start with defining a time from 0 to 100. We're going to get 20 data points, and then we're going to make up some function of y, some function y, which is a function of time. It's just going to have this constant multiplier and an addition of this -1. And then we're also going to type in some hand typed data, just in case you have data in a series that you didn't necessarily collect or calculate. You can type it out just like you would be able to in an Excel file. So if we run this, we're going to expect an array of times, an array of y, an array of this Fibonacci sequence. And then from there, we can create a data frame using this pd.dataFrame. We actually are going to create a collection of all of those three arrays, and that's going to be horizontal, so it's going to be time on top of y on top of Fibonacci, and then this .t transposes it to make it look like the normal Excel table that we would expect. So a column name with time, a column name with y, and a column name with Fibonacci. And here we're going ahead and labeling the columns in the same order that they are in this array. And then that data frame we're going to assign to the variable df, which is pretty common for a temporary data frame, or one, if it's the only data frame you're going to use, it's a simple name. And then we're going to display just the top 5 rows of that data frame using this .head with a parameter 5. Now the default parameter here is 5, so technically this will do the same thing. You can specify any number in here. I did 5 just to be explicit, but as you can see, we have the time series, which starts at 0 and goes in increments of about 5 up to 100. And then we have our y data series, which is the time value times m plus b. This first value is -1. And that also corresponds to this Fibonacci sequence of 0, because that's the first value in this. And then you can see as we step through, we're going down the Fibonacci sequence, we're increasing in time, and we're increasing in y because this is a positive function of time. This is simple arbitrary data, but you can see this kind of looks like an Excel file, right? We have the number of rows and some column names on our data. An alternative way to this np.array with the transpose is to create a Python dictionary, which is just another data structure where we can assign the column names and the arrays like this. This will preserve the data types. So if you notice here, the Fibonacci sequence values were integers. They did not have any decimals, but when we created our data frame, it defaulted to a decimal. And this isn't always important, but sometimes it is. This Python dictionary will keep the data type that this originally was. So rather than specify the columns and do this transpose, we're just going to pass it the Python dictionary and recreate this data frame. And I decided to use the tail function. So we're going to display the last 5 values instead of the first 5 values of the same dictionary. When we run this cell, we can see, so our last time value was 100, which is what we expected. Here's our function of y evaluated at time 100, and there's our last value of the Fibonacci sequence, which is now an integer instead of a float or a decimal. So this has preserved the data types and given us pretty much the same output otherwise. And then another thing, so you can create a copy of the variable or the data frame by using this data frame.copy. There are some parameters that you can put in here as well, that you can look up. This is helpful for in the case where y is a really complex function of t and takes a long time to calculate, or you have a tremendous amount of data that you need to look for. So if you're going to do something experimental on that data, you don't want to destroy your original data or manipulate your original data. So you're going to go ahead and make a copy and then manipulate this second data frame, which will have the exact same values. So that is one way to temporarily store something before trying something experimental if you don't want to have to run previous code and wait for things to come back to you. Another way to make a copy and save it for future use or to share it with somebody else is to save a data frame. So these already look like Excel files or CSVs, and they can easily be saved to CSVs or Excel files. So dataframe.toCSV is going to give us, well, you pass it the file name that you want it to output, and it will save it as a CSV, or you can do to Excel, pass it the file name, make sure that these extensions are correct, and it will save it in an Excel file. So if we go ahead and run this, open up my file explorer, we can see there's now Fibonacci sample CSV, Fibonacci sample XLXX. So in here we can see we've got time, line, Fibonacci, just like we'd expect to see in an Excel spreadsheet. If you open this up in Excel, it'll look exactly like an Excel spreadsheet. You'll notice that there's a column here that doesn't correspond to the Excel index, but it corresponds to the Python index, the Pandas index that we saw with these rows. So this this index here is different than Excel index, and the same thing is in the CSV. So in here, there's a row of these identifiers that don't really mean anything other than that's where they used to be inside Pandas. And the way that we avoid that is to set index equals false when we save these data frames. So I'm going to go ahead and close this. You can run this cell again. Now if we look at this CSV, we've dropped that row, that column that meant nothing. It had this old index of what it used to be in Pandas. Most of the time you won't need this index and can just drop it, because when you read the CSV later, you'll just get a new index that'll just apply to all of the rows by default. And then another neat thing is we might not care about the Fibonacci sequence, for instance, and we might only want to save certain columns of a data frame. So we can specify the columns that we want to save. I'm going to go ahead and run this. And we can see over here, we no longer have that Fibonacci sequence column anymore. So we've only saved the data that we told it to save. Okay. From there, the next intuitive step is to be able to load a data frame from a file. So I have some air quality data from a sensor that we're going to read in from this CSV. So there's a ton of data in here. This is months worth of air quality. It's got a whole bunch of parameters. We're looking at the humidity, temperature, pressure, some particle counts, and then later on there's some particulate matter actual values, as well as a timestamp. We'll get into all of those values a little bit. But here we're just going to do pd.read CSV with our file name, assuming that the file is in the same folder. Otherwise, we need to specify the entire path to the file. And that will give us, we're going to stick that in the AQ data frame. And then another nifty thing is you don't always need, you might have an Excel file that has multiple sheets on it. So like this sample pairs file that you'll have has an updated and an original sheet that has different values on it. So when you do pandas.read Excel and specify an Excel file, you can give it a sheet name and tell it which sheet to read off of. So we're going to keep these data frames different. We have an updated data frame, which takes from the updated sheet inside sample pairs. And then we have an original data frame, which we'll take from this original sheet inside there. So when we run this, we'll get two different data frames, one that will hold these values and one that will hold these values. And then finally, this air quality data frame had a ton of information that we don't really care about. So this is kind of like the same as saving only certain columns. We can also read only certain columns of a specific data frame. So for the remainder of this example, I'm only going to care about the humidity, the temperature, the pressure, the time, some of these particulate counts, and the particulate matter concentration values. And we're going to specify which columns we want via the use calls parameter when we read the CSV. So this takes in an array of strings or whatever identifier is being used to specify the columns. And now our AQ data frame is going to only contain these columns. And we're going to display some of the information that's in these and some of the important factors that are in there. So to begin, it's always helpful to know what columns you have in a data frame are. So I know that we just specified these, but if you hadn't specified these, you might forget what one of these columns is actually named, and you want to be able to go back and retrieve the data that's in there without having to open the CSV and then type code and then open the CSV again. So you're able to see the columns in a data frame by just doing dot columns. We can see we got timestamp, humidity, temperature, pressure, all these that we specified up here. And then something that we've already seen that I've already showed a little bit, this dot head function. So if we only specify 3, it'll give us 3 rows back. Go ahead and run this. So it's given us the first 3 rows of the data frame. This is helpful for if you need to know, like, okay, what units my temperature might be in. I can just go and look and see, okay, this is probably not Celsius. This is probably Fahrenheit that we're dealing with. A good way to just go look at initially what your data looks like so you can easily go and access it later. Likewise, if you only want to see a single column, what you're going to do is index the data frame. So when we index a data frame, we can use certain methods that I'll go over later. If you only want to display a column or a range of columns, though, you're going to go ahead and do double square brackets. And on the most inside square brackets, you specify the exact column name. Now, if this column name is not found in the table, you're going to have problems. So that's why it's helpful to have these data frame column calls, because you can just go and copy and paste this value straight down into here. But here we'll display only the humidity column values for the first 3, so we can see that these match. And we've ignored all of this other data. So if we only want to see humidity data, then we can just specify we only want to see humidity. Another way to do that, which is not recommended, but is possible, is to use this air quality data frame .humidity. So instead of this notation where we're going to use a string, we can just do .humidity .head. And the reason why this is not preferred is when you have a column that has a period in it, Python will not know how to handle this column. It will not know what to do with this information. So you're unable to, I will show an example real quick. You're unable to do something like this. Python does not know how to handle this situation because it's looking for a column that's named 0 that has some other parameter, 3 micrometer count B, which does not exist. But if we were to use this in the case of the string, this would work just fine. So if we drop this right here, we can get our column name exactly back. So this gives you more freedom with what you can name your columns. If the data is not yours, you might not have the ability to choose what's in the columns without renaming them. So this is just the easiest way to go about displaying any amount of data that you might that you might need. However, this is still a viable option if you prefer. Next is if we want to display several columns. So say we only want to look at the humidity, temperature, and pressure. We're going to take the same syntax that's up here, and we're simply going to add other column names that we want to see. So this again is only going to display the first 3 rows of these columns. And then we can see only the humidity, temperature, and pressure of those first 3 values. So this is pretty helpful if you care about more than just a single column, but you don't want to see the entire data frame. And then similarly, if we only want to see a specific row and not a certain column, or we want to see all of the columns for that, we're going to use this function called iloc, which is the index location. And then likewise, it has the double square brackets. And this is useful for later on if you're going to specify multiple rows. You can just add commas in here. You don't have to worry about anything. So this just gives us row number 0, which is the index that Python assigned, that Pandas assigned the data for us for free when we read it in. It's the same index that we're not going to save when we save our files. And then if we want to see several rows, we can go ahead and specify which rows we want to see. So for whatever reason, if we want to see rows 0, 5, and 353, we're just going to go ahead and throw some commas and any other rows that we want to see in there. It'll spit them all out for us. Note that all of these display functions, when they're just displaying straight to Python, they only work for about 30 rows before Python will truncate the output. So for instance, if we don't specify this and we want to print the entire data frame, Python will just give us these dots because it's just too much information to display all at once. There's 359 rows in here, so rather than make you scroll through all this, it will just truncate the values and give you a default. It'll give you the head and the tail of the data frame. But for now, we'll keep it at iloc. The next thing to take a look at is if we only want to see a specific row of a specific column. So in this case, we're not going to use iloc anymore because we are worried about more than just the index. We're just going to use location, LOC. The first specifier is the row number, the index that we want to see, and then the second specifier is the column. So if we want to see what the humidity was like on row 1, which is not the first row in the data frame, remember, that's this value right here. I'll print it out. So row 1, humidity, printed this value. Likewise, if we want to manipulate that value, this is the syntax that we're going to use. So if for whatever reason we wanted to update the humidity on row 1 to be a new value, we would just write equals whatever our new value is and run this cell, and this value in the data frame will be updated. More on that later. For now, let's move along. The same thing, but we're going to display multiple columns. So rather than give a single column name, we're now going to give an array of column names. It's going to give us all of those columns, the first row of all of these columns. So we have that same humidity. And if we scroll up, we can see this is the temperature, this is the pressure. Those are the exact same values that we're getting back. And then likewise, if we want to see multiple rows and multiple columns, we're going to give an array of rows and an array of columns that we want to see. You can go ahead and run this. You could do the same with an array of rows in a single column if you wanted to. But this should cover everything that you should need to be able to do in terms of displaying data. Another important capability of data frames is to be able to display the statistics of certain values. So for instance, if we want to see the average value in the data frame, then we're going to be able to use this .mean function. Now it's important to understand that to use this, we need to know what axis we want to average across. So if we want to average across the rows, we're going to use axis equals 1. And if we want to average down the columns, we're going to use axis equals 0. That's generic for all operations in Pandas that need to determine whether you want to do them row-wise or column-wise. And this value actually for our case doesn't make any physical sense. So if we take a mean across the rows, remember we're taking a mean of a timestamp, a humidity, temperature, pressure, these counts, and these particulate matter concentrations. So if I calculate the average of all of these values, physically does not mean anything to me. So I don't want to take the row average. I want to take the column average. But for now, I'll show this is the row average, which is a huge number because the timestamp is a huge number. And this is the column average, which makes a little bit more sense. So the average timestamp might not mean anything to us, but we can see what the average humidity was, the average temperature was, the average pressure, these average counts, the average concentrations. So most of the time when we're using .mean, we're going to use axis equals 0, which will give us a mean down the columns. At the end of the column, it'll just spit out this mean value. Now, this isn't saving data anywhere. It's only displaying it. But we are able to save this data if we assign a variable on this side. So we assign a var. Then we can access var it'll be indexed just like a data frame where we can just use the double square brackets and timestamp to go grab this value. It'll be a data frame with a single row. But for now, we'll just display it out to the screen. Okay, another thing is the length or the size or shape of a data frame. So most of you are probably familiar with length. It's the same thing you use for an array. Length will return the number of rows in the data frame, regardless of not a number values. And all of these functions are somewhat similar, but not exactly. So let me comment this out real quick and show dataframe.count along down the column. So it's going to count down the columns and give us the row count for each of the columns. So notice that timestamp we only have 358, but humidity we have 359. So we have one more row, but this only gave us the values that are not a numbers. So only the numerical values were reported back with this .count value, which means that we have a row somewhere in that data where it didn't have a timestamp or a temperature or pressure or these B counts and concentrations. And it could be on different rows, it could be on the same row. We just know that there's at least one row that is missing those values. So count gives you the number of not a number values in each column. And then shape is somewhat similar to length, but it will also give you the columns. So shape says there's 359 rows and 10 columns in this data frame. Okay, the standard deviation. So same thing, we have to specify. We want to take the standard deviation down the columns. And the change in degrees of freedom is equal to 1 by default. So in class, we've already gone over why we need the change of degrees of freedom to be equal to 1 for the standard deviation. Here, you don't have to specify it. In NumPy, you do have to specify it. But here, we can be able to see the standard deviation of each of these columns. So once again, the timestamp likely means nothing to us. The humidity, temperature, and pressure, however, and all these counts and concentrations, we now have the standard deviation and the mean. Likewise, there's other information we can get out of these. So the minimum value and the maximum value. And a lot of these are returning these single row data frames. You can actually get all of this information, so the min, max, standard deviation, mean, and count, just by using this data frame.describe method. This will bring you back a data frame describing all of the data. So here we have the count. There's 359 rows that have humidity. There's only 358 that have temperature. Here's the mean of each of these. Here's the standard deviation, minimums, the quartiles, 25, 50, and 75%, and then the maximum. And this can actually be saved to a data frame, again, and indexed just like a regular data frame. So we'll put in a temporary variable for right now, and then we should be able to see, if we only wanted to see the column timestamp, then we now have the count of the timestamp, the mean, standard deviation, etc. So you are able to save that data. For now, we'll just print it out to the screen. In case you needed to manipulate any of these values or find cases where perhaps your mean was greater than 40, you'd be able to go and run code on that data frame if you needed to. Okay, speaking of, it's important to be able to display data that meets a conditional criteria. So if we want to know all of the days or all of the times at which a humidity was recorded, which was greater than 50%, we're going to need to have Python run true or false for these. And we wanted to be able to do that without a for loop. So Pandas has this really convenient method of identifying the column, so indexing the column that you want to specify. You can give it a truth, something to test on, just like you would in any other if statement. And this will actually give you what's called a truth series back. So it'll respond true anytime that the humidity was greater than 50 and false otherwise. So we can see we have 359 rows here where they're true or false, depending on what the humidity was for that row. And this in it by itself is not all that helpful, but we're going to go ahead and plug this exact code in to our data frame. So as you can see, this is the exact same as what we have right here. And we're going to take our data frame and then index it where true. So this is only going to give us the rows where this returned true. If we run this, you can see we didn't get rows 1, 2, 3, or 4 because they were all false. We got row 0, row 8, row 12, and then we also got these last 4 rows in here. So we got row 355 through 358, because all of these were true. And looking at this data, we can see the humidity was only greater than 50 in all of these values. Here at the bottom is a convenient way to not have to use the length. If you don't do data frame.head or tail, it'll just display how many rows and columns you have. Especially when it truncates these values, it's very helpful. We can see that of the 359 data points that we have, 101 of them had humidities greater than 50%. So this is a pretty helpful way to find sets of data that meet a criteria that we need. Likewise, we can expand this to be not only this condition. So this is the same condition down here, but perhaps we want to see where the humidity was greater than 50 and the temperature was greater than 78 degrees. So just like in an if statement, we're just going to use this and operator. And then I find it's very helpful to wrap your conditions in parentheses. This will keep you from making mistakes in the future. This can get very complex if you're looking at more than 1 or 2 things, and it's going to be very helpful in troubleshooting later on. So if we run this, we should expect to see less equal to or less than the number of rows that are in here, because we're looking for humidities and temperatures. we can see right here, this temperature was not greater than 78 degrees, and we'd expect that row 0 be dropped when we run this code. When we run this, we can see, okay, there's only row 69 and row 119 where the humidity was greater than 50 and the temperature was greater than 78. So there's only 2 cases in all of our 359 where those criteria were met, and these are those 2. Similarly, we can do the OR condition. So if we only want to see the temperature was greater than 78 or the humidity was greater than 50, we expect a greater than or equal to number of rows than this value, because now we can have either condition be true and it does not have to be both. So we can see that here, 283 out of the 359 were true. So this humidity was less than 50, but the temperature was greater than 78. This humidity was greater than 50, but the temperature was less than 78. So we got both rows back because we only cared about one or the other, or both. Okay, the not operator is different than in an if condition. The not operator for a truth series is this squiggly character that's above your tab key. Once again, a good reason to use parentheses right here. This will reverse all of the values that this truth series gives you. So it is the same as false, true, 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 false, true, false, 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 and all of the middle part that got sliced out of this truth series. So we're going to look for days that the humidity was not greater than 50 and the temperature was less than 78. We can do that right here. There's 76 rows, so the humidity is always less than 50. This might not be the easiest. This might not make the most intuitive sense to use for a case like this. We could just use the less than equals to over here to accomplish the same purpose. But these truth series conditions can get very complicated. For instance, if you're looking for a string within a certain column, if we had a column here that described air quality and just said the air quality was bad, the air quality was good, the air quality was moderate, and we were searching for days where it said bad, or more specifically, days where it did not say bad, it would be easier to add this not operator than to add another condition where it was looking for good and moderate. So this not operator can become helpful, but most of the time you should be able to just flip the logic on these numerical values. Okay. We can also display data that is in a special set that we prescribe. So for instance, if we only want to see days where the humidity was exactly 40.182, 43.5, or 42.214, we can use this is in method. So we're going to wrap our condition in parentheses. We're only going to look at the data frame where it is the humidity, so only the humidity column, and then use this special .isIn method and pass in that array. So right here we can see, and you can see that I've just fabricated these values. In this array, I've just gone and grabbed some rows that met these conditions. But it returned all of the values where these humidities exactly were reported. And likewise, you can use this not operator here and get everything but these 3 rows. So we've got 356 rows instead of 359. A slightly better example might be, well, to show that this is looking for any rows that meet these criteria. The Fibonacci sequence that we defined earlier had 2 1s in it. So we use the same thing for that data frame that had the Fibonacci sequence and time and a function y. And we'll get back 2 rows in the Fibonacci sequence that had 1. because it's looking for any row that meets the criteria, either is equal to 1, is equal to 2, or is equal to 3. This is a simple way of checking multiple conditions instead of writing or statements for all of these possible values. You can just use this is in method really easily. And then similarly, if we're looking for not a number values, then we can use the is and a method. So if we're going to look, if you remember, we had 359 rows of humidity and only 358 rows of temperature when we use the .count method. So we would expect that one of the temperature values is a nan, or not a number. And when we run this code, this is looking for the data frame column where it's temperature and if any of the values are not a number. And sure enough, we have a row where row 85, our temperature was not a number, pressure was not a number, timestamp was not a number, and all these B values were not a number. So this is the row that was I added in to fabricate. Our sensor did not respond properly. And as you can see, we also have this invalid value of humidity greater than 100%. So likely our sensor crashed and something bad happened to it. And we're going to need to figure out how to deal with all these values, all these not a number values. So I'm going to go over some of the ways that you can deal with them. They're not necessarily the best ways in actual practice to deal with these values. Every case is going to be different. You're going to have to think about the system, think about how you should treat this case. But for our purposes here, I'm just going to show how we can replace some of these not a number values, how can we replace these invalid values, and what we should maybe do with this row going forward. So cleaning up not a number data from a data frame is going to be important because in the real world there are times where your sensor won't respond and you're going to want to just remove all the rows where it doesn't respond, for instance. So using our dot location, we're going to actually replace this humidity with np.nan. So this is the same value that's in the array right now. numpy has the not a number value, very easy to access just like this. So we're going to set where the row is equal to 85 and the column is equal to 123.4. Oh, sorry, the column is equal to humidity. We're going to change this value 123.4 to be a not a number value. And then we're going to display rows 84, 85, and 86 so we can see how this data frame changes as we go through these next steps. So here we've lost this value of 123.4 and is now not a number value. So that's helping us when we take our average, if we need to take an average later on or a standard deviation, then we don't have this invalid value that's making our humidity look higher than it actually is. Another way that we could handle this is we could say, okay, like I don't want to drop this row completely because it still has some good data. It's not all good data, but I don't want to lose this information, this little bit of information that it did pass back. But I also don't want to think that this humidity is a possible value. So there's most operations that Pandas is built in for you will not be able to deal with not a numbers, or it'll just completely ignore them. But if you're writing code on your own, you might want to say, okay, I'm going to set these to -1. And then if I encounter a -1, I know that I need to ignore that value. So this would not fix your problem in the case where you need to take an average, but you can replace them with some other value. Likewise, the other way around is if your sensor brought back a negative value here, you could replace the negative value with not a number. So this could go either direction, but we're going to replace in the column humidity, we're going to replace not a number values with a -1. And I'll go over what this in place means down below. This is pretty much saying I want you to perform this operation on this data frame without giving me a new data frame or without copying my data. And I'll go over this in more detail later on, but we're going to do the same for the temperature and the pressure rows. So all three of these values we're going to replace with -1, display the same data. There we go. Now, if we have a condition that checks if our data is -1, we know to ignore it, which would be the way to do things by hand. But most of the time, Pandas will just ignore these values for you, and you'll be better off leaving them as not a numbers. Just wanted to show the functionality of this dot replace method. Okay. Likewise, later on, if we're going to take an average of our A node and our B node inside the sensor, and A reported a value, but B did not, we need to know what the value of B was in order to take that average. So for this example, we're going to copy A's data into B, but only where B is not a number, which is a little bit tricky because we don't want to just copy all of A's values into B, or we're going to have only A's values in here. We don't want to lose this value and replace it with this one. We only want to remove this not a number, these not a numbers with the corresponding A value, which can be accomplished with this fill NA method. So we're going to take this column right here, use the dot fill NA, and replace it with the A column of the same count. Likewise, we're gonna use the in place again here, and then we're gonna perform the same operation for the 5 count. So run this, we can see, okay, now B has not lost its data before when it already had a value, but when B was not a number, its value has now been replaced with the value that was an A. Same thing has happened for the 0.5 count. And we didn't tell it to do that for the particulate matter or any of the other values. So here we still have not a number to deal with. So all of these were just examples of how to replace certain values or how to fill certain values with other values, only when they're not numbers, which are both valid things to do when you need to replace not a number values. In our case, the best thing we can do is actually to drop the rows. So I'm actually swap these. So drop NA will drop anywhere that there is not a number value from your data frame. So let's take a look at how this works. We're going to specify a subset and say anywhere where this column has a not a number value, we're going to drop the row. So anywhere where this column has a not a number, this row should go away. This entire row, we're just going to throw it away. And this actually will not drop anything because we actually just filled this B count with A's value. So if we take a look at this, we can see, okay, that didn't do what we wanted it to do. It didn't drop this row. And that's because we had already filled the value. So if you use drop on a subset that doesn't have a not a number value, you won't lose all your not a numbers. So if you wanted to preserve this value as not a number, but you couldn't deal with any not a numbers in this column or this column, you'd want to use this subset. Otherwise, if you can't deal with not a numbers anywhere, you can just remove this subset entirely, and any place where a not a number value shows up, the row will be completely gone. For now, let's go ahead and drop where the particulate matter value is not a number. So this will actually remove this row entirely. We're going to notice something a little bit strange here. Run this. We have now an index of 84, 86, and 87. So we got rid of this 85 row, which was this bad guy. But now when we tried to index row 85, it brought us back 86, and 86 brought us back 87. So that's going to be a problem in the future if we want to display these rows correctly, or if we're going to loop over these rows and do an operation or try to index something. We're going to expect a value at 85, but row 85 doesn't exist anymore. So we're going to take care of that right now. Um, so another way to use this drop NA is if any value is not a number, we're going to drop that row instead of specifying this subset. We're going to do it in place, so it's not going to return anything to us. And then we're going to reset the index. So we're going to go ahead and drop the old index. It's going to forget about all these values, and then it's going to do that on our data frame without returning anything back to us. So all of these values we'd expect to go back to normal. And we have from 0 now to 357. So row 358, which used to exist, now does not exist. And if we look at this same series of data points, we now actually get back rows 84, 85, and 86. So now when we use this ilog function, it's performing like we expect. So reset index is something you're going to need anytime that you remove data from a data frame. Very helpful. Also, if you we're gonna see another case of this reset index down below when we sort through a data frame. It's going to change the position of these rows, and they're going to not make sense to us anymore. So we'll also reset the index in that case. So to be able to add data to a data frame is another important functionality. So we're going to use the same code that we used before. This new time2 is going to be the reverse of our original time. We're going to calculate a new y2, which uses this time2, the same formula. And then Fibonacci 2 is also the reverse of the old Fibonacci sequence that we had above. So we're going to create a data frame from that data using this np.array that we used before. We've got time and then y and Fibonacci, and then we transpose it, which shifts the columns to the rows and swaps them. And then the columns are going to match the original data frame columns. So this will make it very convenient because the original data frame columns are time, y, and Fibonacci. And we want that data to match exactly, so we'd expect them to have the exact same columns. And we're going to use this pd.concat to combine the original data frame with this new data frame that we just made. So when we use this concat, it's going to spit back two data frames stacked on top of each other. So let's take a look at that and see what that means. So right here we have the original data frame. We have time, y, all the way the entire function, the Fibonacci sequence. This is the original data. If I keep scrolling down, we now have all of this new data, which is the reverse of the same data. So you can see it goes from 100 to down to 0. It applies the opposite function, and the Fibonacci sequence goes in the opposite direction. But you'll notice that it stacked the data frames on top of each other. So the index is now 0 to 19 and then 0 to 19 again, which is not very helpful because if I want to take a look at dot location 0, it should return either this row or this row. Let's see what it does. So it only returned the first instance of the index being 0. And if I wanted the time where the time was equal to 100 in this other row down here, I now cannot access it. So when we concatenate data frames, most of the time we're going to use this ignore index. And that's just going to say, I don't care what the old index was in this data frame. I don't care what the old index was in this data frame. Just go ahead and give it a new one. Now when we run this, we're going to have 0 through 19, and then it proceeds on 20 through 39. Now we can index this data exactly as we would expect. We can go and get row 20 instead of the second row 0 to get this set of values. So that's concatenation, creating another data frame and then adding it onto your current data frame. Another thing that might be useful is adding a new column to a data frame. that already exists. So this air quality data frame, we had this timestamp column in here, and we want to make that into a real human readable date time. So we're going to use this pandas method, pd.toDateTime. It's going to take the timestamp that existed, which was in units of seconds since UTC start, which we're going to specify the unit as seconds. And this notation is going to create a new column, date time, filling it with this data. So let's go ahead and run this. I'm only going to display what the timestamp was and what the date time is. We can see it's taken this timestamp, which was this big ugly number in seconds, and turned it into a date time that we can all understand. So July 12th, 2022 at 6 a.m. We can see here the index in these rows does not match the date order. So we have these two dates in July, and then we have this date in June, and it doesn't match the index. So we might care that this data comes in order with respect to time. And we're able to sort this data, and that'll be the next thing that I show. So we're going to use a sort values method. We're going to tell it what to sort by. So it's going to sort by the date time column. And then we're only going to, this is going to return a data frame to us. And then we're going to tell it to show only the timestamp and the date time columns. Once again, let's take a look and see what this looks like. And then, like I mentioned earlier, these indices, even though we specified head, which is supposed to print the top of the data frame, is printing now 211, 226, and 343. So we can see that these date times are in order now. They start on June 1st, 6 a.m., then 12 p.m., 6 p.m. So this did what we wanted it to. But this index is messed up. We would expect this to be 0, then 1, then 2. But it's preserved the old index of these values because we haven't told it to reset the index or to forget about the index. So the next method, this also did not save the changes. So this is displaying a data frame. If we assign a variable to it over here, then this variable will hold the sorted data frame that's returned by this. It's only displaying because we didn't save it, and Python just spits it out as output. But if we want to save the changes, we're going to do something like this. This is where the in place happens. So this code alone is actually going to return nothing. It's going to perform all of the operations right on the air quality data frame, and it won't give us a new data frame to look at. So if we run just this code, nothing will be printed out because it returned nothing. If we assign a variable here, and then we try to print that variable, it says none. So whenever you use in place is equal to true, the data or the operation that you're specifying is going to be done and accomplished on this data frame. Nothing will be returned to you. So this variable is none. But the actual data frame will be changed. So if you want to make a copy of the data frame where the copy is sorted, you could call it sorted air quality, and not use this. That is one way to make a copy of this data frame. This data frame will not be sorted. This data frame will be sorted. But if we use in place equals true, once again, this will be none, and this data frame will be sorted. So kind of depending on what you want, you can specify the in place variable. Most of the time, you're going to use in place, assuming that you're confident that you want the places that you want that operation to take place forever in your data frame. So let's take a look at this now. This will give us the same thing as before. So as this line up here did. But the only difference being now we have saved the data frame and then we have to tell it to display later. So the actual data frame changed when we use this in place equals true. This is, I prefer to use this method for saving changes. The alternative way is to give it the same name and not specify in place. So this is a little bit harder to remember than just saying in place equals true, in my opinion. And you can also have a mistyped variable. So if you do something like this, then you're not going to get back what you expect because data frame one, AQ data frame one, is what's holding your sorted values, not this AQDF, like you might expect later on. So not preferred method of saving, but another option. Moving on, we have a way to update and fix this index. So like before, we use the reset index. Drop tells it that we're going to completely remove this old index. We're going to completely forget about it. We're going to do it in place. So this actual data frame is going to change. When we display this, okay, now we have June 1st at 6 a.m., then 12 p.m., then 6 p.m., 0, 1, and 2 for index. So now it's sorted and our index matches the sorting that we specified in the daytime. Alternatively, we can do this all in a single line of code. So all of this sort values that was done up here and all of this reset index can be done in a single line of code by sorting the values by our parameter and just specifying that we want to ignore the index. So when it reshuffles these items and sorts them, it won't remember what the old index used to be. It'll just give it a new index and completely ignore it as if it never existed. So we'll do the same thing here. I'm actually going to sort them by pressure. And so I'm going to specify the pressure. We see the pressure at the end as well. So if we wanted to sort by pressure, we now have the smallest pressure followed by the next, followed by the next. These indices were updated because we now have dates out into August that are assigned to these values instead of these values that were in June. So we've ignored that the index existed and just assigned it to whatever we sorted the values by, which probably makes more intuitive sense. Okay, creating an average column. We've kind of already talked about this with creating, looking at the statistics of a data frame, but we may only want to perform a math operation on 2 or 3 columns and store it into a new column. So we're going to take this data frame and add a new column, which is this count. It's 0.3 micrometer count. And it's going to be the average between nodes A and nodes B. So we define the average function ourselves, which could be any function. If we weren't looking for the average, for instance, and we wanted to calculate from here to a concentration, we could apply any function over here. And this will take each row and apply this function to it for us. So we don't need to write a for loop to do this. We can do it all right here in one line. This is the same as typing like this equals into Excel and selecting the cell and dragging it all the way down the column. So adding this formula in and dragging your formula all the way down to the bottom of your file. So it's going to take this A count plus this B count and just divide it by 2. So a simple average. Let's take a look at it. So let's take, just for some verification here, let's take a look at these original values. And we can see, okay, now we've got an average of this 3 micrometer count between nodes A and B. Likewise, we could take the actual average a little bit in a little bit more complex way. So once again, if we had a not a number value here, this math doesn't know how to deal with not a number. We're not going to be able to divide a value that's not a number by 2. So this math would crash in that instance. However, down here, if we're going to say, okay, I want to take an average between 0.3 to 0.5 counts, then I'm going to take the data frame, specify all of the columns, like we did when we were displaying things. So it's got the double square brackets, all of the columns that I want to average, and take the mean across the rows. So this is an instance where we didn't take the mean across down the columns, because we want to take the average as we move along these rows. So it's going to take the average of those two values and stick it here, rather than take the average of this value, and this value, and spit it out at the end or add it as a so this is actually a case where we want axis equals 1. Take a look at this. We get let's drop these in again, and we'll drop the 0.5s in just so we can see everything. So now we have this average, which is an average of these 4 values. And it will handle not a number values. So if this was not a number, it will pretend as if it didn't exist, add these 3 values, and still divide it by 4. So this will handle not a number values for you in a little bit more friendly way. And like I said before, this could be any equation that you want to apply to that data to add a new column to. And then another thing for updating data frames is we might want to drop an entire column from a data frame. So earlier on, we had a function y, which was a function of t, and we specified a time, and then we specified the function y, calculated it out its values. Then we also assigned this Fibonacci column to it. We didn't save that Fibonacci column when we saved the data frame earlier. So back here, we didn't save the Fibonacci column. We might decide maybe it doesn't make sense to store the Fibonacci sequence next to time data in a function for no reason. So we're actually able to drop that column. So from our concatenated data frame from earlier on, when we added those two together, we're going to drop the columns. This can be an array of multiple columns if it needs to be. For now, we're only going to drop the Fibonacci, and we're going to do that in place. So it's going to just remove the column completely and do that operation on this data frame. Take a look at this here. Now we can only have the time and the y data, which is what we expect. We expected that Fibonacci sequence to be gone. So likewise, we can remove this y data. This actually is going to throw an error because we have already dropped Fibonacci and we did it in place. So this concatenated data frame no longer contains Fibonacci. And if we run this code again, it's going to look for Fibonacci and say, I don't know what Fibonacci is. It's not in my data frame. So we can see Fibonacci is not found in the axis. It doesn't know how to drop it because it doesn't exist. So if we want to just drop y after that, we can go ahead and do this. And then to avoid the same error from happening, if we want to run it multiple times and just see what our data looks like, we're just going to remove this in place. So, and we're actually going to remove this head because we didn't store this into a temporary variable. So it performed this operation, didn't save it anywhere, and then we're just displaying what the old data frame used to look like. So real quick, we're going to comment this out. We dropped column y. Now we see our time. There is no column y. There is no Fibonacci sequence. We added the in place equals true here. It would save our change. But then when we look back at our data frame, now our data is still has our y there because we haven't added that in place equals true. And so it's spitting out right here. We didn't ever save this data frame where it had this dropped y column. So it spit it out, but because there's code below it, Python never displayed it to the screen. So this is one of those cases where you got to be careful if you're going to use in place. Make sure that you want that change to take place on this data frame. Otherwise, specify a variable or make this the only line of code or the last line of code in your block so you can just see what your data might look like. And I just dropped it in place. So that's an example of what just the index of a data frame would look like. But this will just let you see what my data might look like if I were to drop this, versus this will just drop the data for you. So this is another instance where you got to be careful about this in place equals true, or to make a copy of this data frame before you make changes to it, like dropping the columns. Okay. Moving along to our last topic, which is the most advanced, and likely you won't need this in this class, but is a very helpful tool to have later on. If you remember when we looked at this sample pairs Excel file that had two different sheets that had updated and original. Let's take a look at that. So let's go ahead and run this code. We'll bring in the updated data frame and original data frame. And let's just display each of these so we can see them side by side. So this updated data frame has a sensor index, which is an ID, which are just these 6-character long values. We don't really care about what they are. It's just a unique identifier for them. But we can see they have an original pair. These are IDs that correspond to IDs in the original data frame table. So we can see right there we have 36453. Right here we have 36453. So we know this new sensor index corresponds to this old sensor or original sensor index. And we want to compare the latitude, longitude, and altitude of this new sensor and these old sensors. Now, note we have one sensor in this new sensor which has an original pair that does not exist in our table down here. So we're going to have to write our code in order to look for, going to have to check to see what the sensor index is, then go and find this sensor index, and then it's going to have to go and compare these values, do a little subtraction, and we're going to have to store what these values are so we can determine whether these sensors are close enough to each other that we can compare their air quality data. So this is going to be a little bit tricky to do without a for loop. It's a little bit advanced to do in Pandas, but let's take a look at what this would look like with a for loop, just so we can see how complex this problem can be and how quickly it can grow into a big problem. So we're going to take a look at every index in the data in the updated data frame. So for each of these values, we're going to go and find the original sensor index and assign it from the updated data frame location, the row where it says original pair. So on iteration 0, we're going to run and find this original pair, and that's this original sensor index is going to be loaded up with 36453. Then we're going to go get the row of data that corresponds to that sensor. So the original row is the original data frame, where the original data frame sensor index is equal to the original sensor index. So that's going to give us back this row, right? This is the conditional statement that we have in here. So the sensor index where it's equal to this value that we looked up before. And it's only going to return a single row because these are unique identifiers. Then we're going to go ahead and calculate a latitude difference. So we're going to take the absolute value of the updated data frame's location, the latitude minus the original row's latitude. So we're going to take this 38.475 and subtract it from this 38.478. And then same thing, longitude and altitude for that. And then this is just going to print out which sensors we're comparing, what the latitude difference was, what the longitude difference was, what the altitude difference was. Notice our code does not check to make sure that there is an original sensor index that corresponds to this table. So when we get to this bottom row and look up this value, it's going to throw an error because it's going to take this this original pair sensor index. It's going to look in this table and return 0 rows because this number does not exist inside this sensor index. So it's going to return an empty data frame. And when we try to go and find the latitude and longitude, it's not going to know what to do. But it'll print out the first 5 values real quick here. So it's comparing 11063, which is our first updated sensor, to 36453, which is our first original sensor. Latitude difference, longitude difference, altitude difference. Same thing for all 5, the ones that have a pair. And then right when we got to needing to index this row on that last pair, index 0 is out of bounds for access with size 0. So there's nothing in this original row because there is no row that corresponds to that last original sensor index, and it does not know how to compute this math because nothing came back, not a number value. So this can get very tedious to do by hand, especially using a for loop. We'd have to go add in extra logic of making sure that this value was actually in this table before we ran all this logic, and this can quickly become a mess, especially when you're doing a bigger problem than this. So we're going to use a pandas.merge method to solve this problem. Merging is a little bit complex. For anyone that does know, like any SQL databasing, it's very close to a SQL join. But for right now, you can look at the documentation in this .merge function. I'll describe pretty much the gist of what you'll need if you do end up needing it in the near future. So we're going to take, this is our left data frame, is the updated data frame because it's the left parameter. And then the right parameter is the original data frame. So we're giving it both of these data frames. And we're going to tell it how to link these data frames to each other. So we're going to specify how is equal to inner. This is a special keyword that says I only want to keep rows where a match exists in both tables. So if that'll take care of this case right here. We're going to match the original pair to the original data frame's sensor index. So the updated data frame's original pair column must match the original data frame's sensor index. And anywhere that there's not a match made, those rows will be removed. So if there was a sensor index in here called 1, 2, 3, 4, 5, 6, because there's not an original pair that has 1, 2, 3, 4, 5, 6, that row would be completely removed and forgotten. And we will see that with this original pair, 178637, which does not have a corresponding original data frame sensor index. This row will be completely removed when we join these tables. All of the other tables will still remain, and it will become one data frame. So the left data frame, we want to compare the original pair, right? We want the updated data frame's original pair column to match the right data frame's sensor index. So it's going to match the original data frame's sensor index. And then we'll note each of these data frames have a sensor index, a latitude, a longitude, and an altitude. And we need to be able to specify when these two data frames join together, we need to be able to keep track of whose values were whose. So which latitude was the updated, and which latitude was the original. And Pandas will do that for you by default by giving you X and Y, X for the left and Y for the right. But you can specify suffixes. So it's a little bit easier to understand. Okay, latitude underscore U is my updated latitude, and latitude underscore O is my original latitude. So that's how we're going to distinguish between columns when there's conflicts in the column names. So let's go ahead and run this code and see what we get. Notice we're assigning to a new data frame, so we're going to take a look at it. And let's see, this did exactly what we were looking for. So we have the updated column names over here, the original pair, the sensor index of the original value. You can see all of these have matched up exactly. We've lost the row that didn't have a value. And then we can see the original latitude, original longitude, and original altitude. And I'll upload all of this data so you can verify that these values actually got brought over. But for instance, this 36,453 has 38,478. Down here, same thing. And now this is really easy to go and calculate all of this math on, as well as store all of the values. So now in this new data frame, we can just create a latitude difference, a longitude difference, and an altitude difference, set it equal to the absolute value of the latitude of the original, or the updated, minus the latitude of the original. So this is what I was saying. You can create a column with any formula on the right-hand side, and it'll just grab a column for you. So if we run this code, we can just see the differences. So this did everything that print function did, but it also stored it onto our data frame. And now we can go, if we needed to, we could say, okay, any altitude difference that's greater than 10, the sensors are too far apart. We can't use their air quality data. We can't compare their air quality data to each other because they're too far apart. We expect their air quality to be different if they're more than 10 feet above each other in altitude, which likely isn't realistic. But now we have the data. You can go write that conditional series and eliminate these sensor pairs where the altitude is greater than 10 feet. Just to show real quick this how, if we were to change this to outer and run this again, it will bring back every pair plus any value that didn't come back with a pair. So this original pair that didn't have an original sensor index that matched with it, it brought back a row of not a number values in case we want to see all of the data. So likewise, if there had been a sensor index, an original sensor index, 1, 2, 3, 4, 5, 6, even though it didn't exist in the original pair, we would expect another row that said 1, 2, 3, 4, 5, 6, had a latitude, longitude, and altitude, but had not a number values for all of these updated values. So that is one of the other options that you have for this how method. But for now, this is all I have on Pandas. This last little portion is a little bit advanced. You likely will not need it for this class. Everything above it will serve as a good guide to get through statistics and through most of your projects labs courses that you'll take on your junior and senior year. So hopefully this has been helpful.